Hi, good morning, everyone. I hope you're all doing well out there. I hope you're safe and secure. I know it's been a tough couple of weeks for everyone, but we are going to try to move forward and hopefully we can still get something out of the rest of the semester. So, here goes our first video lecture, and I hope it goes well. If you have any questions regarding today's lecture, you can contact me via email, and I will try to respond to those. If you think that's not going to be enough, we can always set up a Zoom office hour. It'll be about like meeting face to face, except for virtually. And I'm also set up a discussion forum on Canvas that you can post to. You guys can respond to each other's questions there. I can also and will respond to those questions as well. I'll try to stay on top of that for the rest of the day. My responses on the Canvas forum might dwindle after that, but I'll try to stay on top of those. All right. So without further ado, let's move on. All right, so here's a question for you. Trying to keep these as similar as we do in class, so I want you to stop, think about this for a few minutes on your own, and go ahead and hit pause. And when you think you have the right answer, you can go ahead and hit play again. All right, so the correct answer here is all of the above. We see large organic molecules everywhere in the solar system. They can be found on all of these bodies. And remember, these organic molecules are the building blocks of life. So this is our first requirement as we look around the solar system, the first thing we're looking for. And the reason we're looking for these, or one thing we might think about, is that 96% of biomass, that's all living creatures, is hydrogen, oxygen, carbon, and nitrogen. And we talked about this back at the beginning of the semester, although it's been a long time. We talked about the abundances of these different things. And as a reminder, these are the first, third, fourth, and sixth most abundant elements in the solar system. That means that the building blocks of life are everywhere. And like I said, when we look around, we see giant organic molecules nearly everywhere in the solar system. They are, one place in particular is in the atmosphere of Titan. This is the largest moon of Saturn. It has a very thick atmosphere, so this is one of the places we'll look. There are reactions that take place with ultraviolet light that create these large organic molecules, and they rain down from the sky. So here's a nice quote from Carl Sagan, that these things are raining down from the skies like manna from heaven. All right, moving on. Here's another question for you. Which of these is a true statement? So again, please push pause, and when you're ready, begin again. All right, the correct answer here is C. That planets closest to the sun receive the most energy because the sun's energy gets less concentrated farther away from the sun we are. And so we'll go ahead and take a look at the next slide for a description of that. So here you can see a picture of the sun down here at the center of these three spheres. And what this is showing is a little patch of sunlight that's moving outward away from the sun. And as the bit of energy moves farther and farther from the sun, we can see that at 1 AU it takes up one of these little arbitrary squares. That means that this amount of energy is spread out over one square. As we get to 2 AU, that same amount of energy is now spread out over 4 of these arbitrary squares, and again spread out over 9 squares as we move to 3 AU. So what this is showing us is that the sunlight spreads over a greater and greater area as it moves farther from the sun. This means that the energy contained there becomes less concentrated. That means there's more energy available close to the sun and less energy available farther from the sun. What does this mean in terms of life? Well, remember photosynthesis. The photosynthesis is likely close to the sun, where sunlight is intense. Places like Earth, we have lots of photosynthesis here. Phytoplankton in the ocean, grasses and trees on land, these things all provide nutrients. Higher and higher up in the food chain, the sun is really the dominant source of energy for all life on Earth. Now, as we move farther and farther from the sunlight's less concentrated. There's not enough energy for photosynthesis. And so, far from the sun, in the outer solar system, that's like Jupiter, Saturn, Uranus, Neptune, way out there, we think that it is likely that chemical energy is the primary source of energy for life, assuming it exists out there. All right, moving on. So I guess before I move on, that's the second requirement we need for life. The first one is building blocks. The second one is energy. And the third requirement for life is some sort of liquid. This is something we've talked about a bit in the past already. So it turns out that water is not the only possible liquid. It's the one we focus on for some very good reasons, but all of these liquids down here are possible liquids that could support life. We see water, ammonia, methanol, that's wood alcohol, methane, and ethane. Now, all of these things are liquids over some range of temperatures. We can see those range of temperatures over here, and you can see that water is liquid over a wide range of temps. Now you may be taking a look at this chart and see that methanol here is also a liquid over a wide range of temperatures. Now it doesn't have some of the other unique properties that water has, but a big problem with this is that there is no known reservoir for methanol in the solar system. And so there's just not really any of it around. All right, so here's our last slide. Again, I want you to take a moment, push pause, and take maybe 3 minutes to write down, in your own words, please describe the 3 primary reasons to choose water instead of one of the other possible liquids that could support life. So what are the 3 primary reasons that we expect water to be the liquid that supports life? All right, hopefully you've gotten something written down now, and I'm going to recap these briefly for you. The first one, as we talked about on the previous slide, water is a liquid at a wide range of temps. Second, solid water floats in liquid water. Now, as far as I know, this is unique to water. Most every other solid are more dense than their liquid form, which means that they sink. Now, this would be a problem if water sunk when it froze. In Earth's past, when we had those large freezing events, the snowball Earth, the oceans would have froze from the bottom up, which means that as they warmed, instead of quickly re-thawing from the top down, we would have to warm up the entire ocean before we froze that ice, and it would tend to build up and build up and build up at the bottoms of the oceans where very little sunlight penetrates down to. So the fact that water floats is very, very advantageous for life. Now, the third and final reason here, which is actually related to the second reason, is that water is a polar molecule. Now, what do I mean by a polar molecule? It has this shape. We have an O and 2 H's, and because of this shape, we end up with a positive charge down on this end and then negative charge on this end. And so we have a negative pole and a positive pole. Sorry, let me rewrite that. A positive pole. Just like Earth has a north and a south pole, a water molecule has a positive pole and a negative pole. That's what we mean by a polar molecule. Now, this allows salts, but not fats, to dissolve. And this is important. Remember the cell membranes of cells? Cell membranes are made of fats. So cells don't dissolve. If we put cells in some of those other liquids, ethane, methane, ethanol, they will simply dissolve because those are not polar molecules. That would be bad for life. It also forms what's called hydrogen bonds. Now, you won't be expected to know the details of these bonds, but these are important for many different organic chemistry processes or chemistry involved with life. And now these hydrogen bonds are also the reason that ice floats in water. This is because as water freezes, it has to rearrange into this crystalline structure that is less dense than it is in its liquid state. All right, well, that's the entire lecture for today. And so thank you very much. Again, I hope you're doing well out there, and if you have questions, please feel free to email me and or post your questions to the discussion forum on Canvas. All right, have a great day.